Paolo Vavassori from San Sebastian, Signa Nobune. He's a basket professor there. The auditory is all yours. You can start
the stage also. Thank you very much. So good morning, everyone. I don't know how many of you were at the talk the other day. So we are going to cover, let's say, all the fundamentals that are behind the Magneto-Optics and magnetoplasmonics topic. So I don't have a specific plan. I have maybe 100 slides that we don't need to go through all of them. Actually, this is I'm recycling a course that I gave last year at the European School of Magnetism. And there I have a kind of 5-6 hours. Good morning. 5-6 hours, and so that's why it's very long, but we don't really need to go through all of this. Maybe I will decide. We'll figure out. Okay, this is the first slide you see is just introduction where San Sebastian is. I got to go up here. San Sebastian is a city of Spain here, this corner of the Iberian Peninsula. This is Spain, this is France, this is the Atlantic Ocean. This is this part of the city, the center is down here, and this is my house. I would like. And this is the center. So this should be low with batteries, but I think it might work. There is enough energy to switch the slides. Okay. So as I said, the plan is to give an introduction about the physics. I gave a very simplified introduction already during the talk the other day. That was really, really naive. Okay, now I will try to go a little beyond that, just to show that I know what we're talking about a bit. Can you see from there? Or? Yeah, it's definitely. And then the other aspect, since I understood that here you are kind of, so the research here that you are planning to build is also here, is very related to magneto-optics somehow. So the plan also is to give hints on how to build the system, what you can do with magneto-optics. So more on an experimental side, how to build a device or a system to measure properties beyond what normally you can do. You can measure hysteresis, you're very happy, but there is more that you can do easily. So that's the purpose. I hope that will be of interest to people. So it's kind of part theoretical and part more on hands-on, how to build the system. Okay. And go through all the possible, some of the applications that have been developed based on magneto-optics. You will see that you can do a lot of things exploiting this contrast that light experience when it gets to interact with the magnetic material. Okay, let's go on, otherwise that was too optimistic. Right, okay. So what is the magneto-optical effect? So it's basically represented here. If you have a metal, okay, and you shine a light on a metal and you polarize the light with some polarization, if the metal is a normal metal, the light which is being reflected maintains the same polarization. It's not completely true, but it's very true, let's say. For us is what we need to know. So the reflection of light or transmission of light through a metal, okay, is polarization preserved. It doesn't change the polarization of light, okay? It's like to say that the polarization modes that you can think of the light, which is the TM and TE polarization, so P and S. I don't know if you are, I can use this terminology, I think I don't need to explain. So P means that the electric field is, good morning.
Hello.
It means that the electric field of the light is oscillating in the plane of incidence. So you send the light against your surface, it gets reflected, so this defines a plane, okay? if the electric field of the light is polarized in this way while hitting, that is called TM light, transverse magnetic light, and we call in optics P-polarized light. The other polarization, perpendicular to that, is called S-light, which would be transverse electric polarization, okay? So these two are modes, eigenmodes of light in space. So if you polarize the light P and S, and you let it go, the polarization doesn't change. In physics, these are called eigenmodes, okay? Because they can survive forever in the medium, vacuum, whatever, okay? It turns out if you have a crystal, which is cubic crystal or a polycrystal, also it works, these are also eigenmodes inside the material. So if you have eigenmodes outside and inside, transmission and reflections preserve polarization. Okay, if you have a metal, you cannot change polarization of light by reflection and transmission if you polarize the light linearly. Okay, and any other polarization, because any other polarization can be developed as a combination of these eigenmodes, S and P. So no polarization change. Now, what John Kerr and Michael Faraday, I should reverse the order, Michael Faraday and John Kerr discovered back already almost 200 years is first Michael Faraday making experiment in transmission from a very thin film. Actually, he was using a glass, because you can see the effect also in glass. That the light being transmitted, if you apply a magnetic field to your material, change polarization. So you have changed some internal property of your material. So these are no longer S and P eigenmodes inside the material. If they are not eigenmodes, you have to have the boundary condition, the conservation of a parallel component of the electric field at the boundary, etc., to be complied with, and then we change the propagation of light, the polarization while the light is propagating in the material. That means it changes the polarization of light when it is transmitted and when it is reflected. Okay, so in sequencing time, before transmission and later on reflection, these two brilliant scientists figure out that light, actually, if you apply a magnetic field to your material, if the material is a special material, you can change the polarization of light. You start from one polarization like this, and you end up with polarization which is normally elliptical. It means that you start with an electric field which has this component. Inside the material, the electric field of the light which is being transmitted acquire also an orthogonal component which is not in phase, and so the light which come out here or is being reflected will be the original electric field plus the one that has been generated inside, which are not oscillating in phase, and the result is an elliptical. So the electric vector of your light is rather than oscillating in one direction, is describing an ellipse in space while propagating. Okay. Polarization of light.
Yeah.
It's okay. I don't need to. You understand what I'm saying. So you have an electric vector which is rotating. If you let the light coming in towards you and you look at what happened to the electric vector is actually, when it's hitting you, is rotating. If it's linearly polarized, the electric vector is doing this against you. Okay. Okay, so if we reason about eigenmodes S and P, the effect of the application of magnetic field is that you start with an eigenmode, and inside the material is generated somehow the orthogonal, the other eigenmode, with a different phase. Okay, so the magneto-optical effect, so this mysterious effect which is occurring inside the material, is a polarization conversion. You come with a certain polarization, and the material generates. So you have to imagine light is being absorbed by atoms, re-emitted, absorbed, re-emitted, absorbed, re-emitted continuously, and that builds up the light propagation, which acquires another component of the field in the other eigenmode. Okay, and that's the effect. So, in other words, if you think that the optical and electrodynamical properties of a material can be described by normally they are described by the dielectric tensor. So this is the response to an electric field of a crystal. Okay, it's a tensor because a crystal in general can respond not. It requires a tensor because you might send a field which is in this direction. You can generate a field in another direction, in all the possible directions in space for a most general crystal on Earth. Okay, and so you have a tensor which is like this. For your metal with no magnetization, this tensor will be diagonal. Okay, if the tensor is diagonal, it means P goes to P, S goes to S. Eigenmodes are preserved. If we have this effect of changing polarization, it means that your tensor, the electric tensor, has to acquire some off-diagonal terms. It's the only way to get a component of field coming along one direction and generating a component of field that has a perpendicular direction. Okay, that's what means epsilon xy. I go in x, p, and something is generating a y electric field. That's the polarization conversion. So a metal, gold, silver, whatever, would have this diagonal, and normally with these three things here equal, so epsilon 0, epsilon 0, epsilon 0, and everything will be 0. If the material is iron, cobalt, nickel, for instance, and is not magnetized, is the same, but when you apply magnetic field, something appears here, okay, and here, with a certain rule that we will see. If you think of reflection matrix, we come later to this, the fact that you have only diagonal elements means that if you, the meaning of these symbols, of this metric, which is a 2x2 matrix, is that RSS means the light reflected as, how big is the field reflected with polarization S when I come in S? How big is the field with polarization P when I come in P? Okay, because the field is reduced by absorption, by other effects. So the fields these are not 1, 1. And normally for a metal, you have only these two things here, and here 0, 0. So it's the same. So if you have only diagonal terms here, you have only diagonal terms here. That means conservation of polarization of light, eigenmodes. If you apply a magnetic field, the material has a certain response to my magnetic field, but actually it happens also to gold or noble metals. You generate somehow these off-diagonal terms in the dielectric tensor, and the reflectivity matrix also develops two terms here that tells that you have a polarization conversion. You go in P and something gets out S. All right. Okay. So this is the same story, and also we have some expression of the. So this is the change I was telling about. So a metal non-magnetized, dielectric tensor is diagonal. You apply a magnetic field in a general direction, and you get 3 terms here. Okay. Additionally. You can have also second order effects, further effects, and changes can occur everywhere, but we are limited to a simplified approach where the effects are bigger. First linear order effect. Why I showed this, which is a repetition of the previous one, because now I show some expression. So if someone wants to work with Magneto-optics, these are something that normally finds in books and papers. Everybody starts from here, because you have an expression on how these elements that are introduced upon application of magnetic fields look like. These are the expressions of the three of these three things here. You see are only three because these other three elements are just the same element change in sign. So these metrics become anti-symmetric. Okay, that's an important point. That means that we are breaking time reversal symmetry, which means that changing the time or propagation direction is changing something in your material. Is not the material is not time inverse conservative. So this is important. Suppose you have your material which is a crystal, normal crystal. You send light here, and for some reason you have some off-diagonal elements, so the material is dichroic. You get light rotated. So you're going like this and you get light rotated. Okay. If you come on from the other side, you have the very same effect. Actually, if you come from the other side, you rewind the rotation. If you have a normal material, okay, that means that the dielectric tensor will be symmetric. And most of the crystals are like that. Also the crystal that you use in your polarizer, in your devices, quarter wave plates, etc., are like that. Okay. If this is antisymmetric, it means if you go in this direction and this rotates like this, if you come back, the rotation goes again the same sign. It doesn't rewind. That's coming from the anti-symmetricity of this tensor and the time reversal breaking, because the magnetic field is a vector that has a specific direction, is breaking the time reversal symmetry itself. So these effects are based on this effect. Why I'm stressing this? Because it's a special property, because you can design a system in which you want to block light coming back from the space you sent to it. So you design a system, you have a laser, you polarize it, and you send it towards your sample, and some of the light might come back. Okay? If it comes back and it gets into the cavity of the laser becomes unstable and you are screwed up. Your measurement will have a lot of noise. So you can make some tricks, change the direction, and make some angle in order to avoid the reflectivity, the reflected light to come back to the same position, but that is let's say, is not ideal, because you are not going through the optics along the symmetry axis, so you generate other effects. You don't want that. What you can do, you can place a material that, under the application of an applied field, you get the light from your laser, it is rotated. So you put a polarizer after your laser, so you get the light through the polarizer. This object that rotates, then you go to your experiment. If some light comes back, this object rotates the light of, let's say, 45 degrees, and then the light back is blocked by the polarizer you put in front of your laser. No light back reflected is getting to your laser. This is called optical isolator. And optical isolators are like valves, so like this time reversal symmetry. And there are key elements in optics and requires the application of magneto-optical effects. These are the only optical effects that make the crystal anisotropic, but in a special manner. There are many crystals in nature that are anisotropic, so they change the polarization of light. They are, S and P are not eigenmodes by nature, because the crystal structure is designed. But they are reciprocal. They are not useful to do this operation. Okay? All right. So, beside that, this was a long parenthesis. Okay. The expression here was put just to show that these elements that are coming in when you magnetize are proportional to the direction of M, magnetization that you induce in your material. I hope I don't have to say what is a ferromagnet. Okay. So, when you apply a field to a ferromagnetic material, you develop a magnetic moment per unit volume. Okay. This magnetic moment has some direction respect to X, Y, Z you picked. Okay, these are the cosine of mx along, so the cosine of m respect to the x-axis, the cosine of m respect to the y-axis, and the cosine of m respect to the z-axis. So these are the direction of m respect to the crystal axis. Okay. And this number here is called the Voigt coefficient that tells you how strong is the effect for your material. So Q, the Voigt parameter or coefficient, tells you how big is this polarization change, and the dependence on the direction of the magnetization comes from these cosine directors. Direction of m respect to the actually to the x, y, z, which are defined in our case by the plane of incidence, which is the x, y plane, and the z is the perpendicular to the surface. Okay. So if you from here apply the Maxwell equation, so you send light to a material, you apply the boundary condition, etc., you can calculate how the amplitude of the field which is reflected with a certain polarization is respect to the initial polarization, etc., etc., and you get the reflections matrix. Okay. Because we don't work with this. When you do experiment, we do transmission and reflection. So this is linked to this, but this is useful, the most useful expression. This is what you use to do the calculation. You want to calculate transmission and reflection. I'm showing only reflection, but transmission have a very similar expression. So this is a key point because you see that RPP, so the amplitude of the phi of the field reflected p-polarized when the ions go in p-polarized, has this expression. RPS means what is the amplitude of the field which is reflected with p-polarization when I went in p-polarized. Okay? So this appears only when I magnetize. RSP is just RPS change in sign. This is wrong, sorry, forget about this. RSP has this expression. And RSS doesn't depend on magnetization. Okay. What I said before is in a special case. Okay. So from here, that would be the end of the story already. All the rest is how we measure these things, because here we have the full information. So if I do an experiment where I can measure reflectivity, okay, if I design, that's the optical work that you have to do, design a system capable of getting the components of the reflected matrix you want to. For instance, if I design my optical system to pick this component, I will be measuring mx, so the projection of m along the, and reading and saying something different, my, along the y direction, okay? So if I do an experiment where I pick this element, I will measure this difference. If I do an experiment, etc., I can measure this. All right? So the full job, let's say, for us later on will be to design a setup using polarizer, wave plates, modulator, whatever you. So that infinite way to do that, but not the best way. I show the way I know. Okay. That are used mostly in the laboratories. But the purpose is to get this number out. And actually, you can do also the most brutal approach, where you do just an experiment where you measure reflectivity, changing the polarization of light along the one direction. He has an experience. It's called Generalized Magneto-Optical Ellipsometry. So you do an infinite number of measurements to get this number with a maximum precision, and you can do that experiment. I'm telling this because so I need to measure 3 numbers, let's say, you know, and then to do, actually they are complex, so there are 6 numbers. You can imagine infinite way of doing that. You can do the experiment where you measure the reflected light with one polarization, then you tilt a little bit, so you accumulate a large number of of measurements, knowing by normal optics how should change the reflectivity as a function of angle, then you fit your measurements to this expected law, and you can get out this number with a precision that you, in the end, is limited by the noise of the detectors in principle. It might take a week to get the numbers as precise as you want, and then you have the full information, okay? I don't talk about that. We talk as, you know, like a lazy guy who wants to, he has an experiment, I want to measure, he wants to measure the lazy guy. He wants to measure a component of magnetization. He doesn't need to measure everything at full precision. So this lazy smart guy designed the experiment to get just the component needed for the physics he's about to study. Okay, that's the approach.
One general question about Q. Q in this expression is the response of the material, right?
Right.
So it has to be the same for the...
No.
No.
If you have a Q, it's related to the symmetry again of the crystal. So it's a good question. So the question is if this Q is one number for all the direction of n. Okay? It's just a number for all? No. It might be a number which is different for one direction and not for other two, or for the three direction, depends on the crystal structure symmetry. So if you have a cubic crystal, these three numbers are the same. If you have an hexagonal crystal, you have two numbers, x and y. This and this would be the same because it refers to the plane of the hexagonal unit cell, but the other could be different. If you have a crystal which has a strange point symmetry, you can have these numbers different. The other point to consider, that before I forget, that these three numbers depends on the wavelength. You can even change sign. They are complex numbers. Okay, so this is a cosine of an angle, real number. This is the cosine of the angle that magnetization is doing with respect to the z-axis, etc., and y and x. But Q has to be a complex number because it's the only way to generate a phase delay. Okay, so it normally has a Q prime and Q second. And these numbers depend on wavelength. Can even change sign. This is an important point because you will see if I get beyond slide number 3. But I think that is, I mean, then I can go quicker, but I think that this part is, if you know this, then everything is easier. Okay, I'm making the decision. So, this is something I put on the other day. So, now we want to spend 5 minutes, that would be 50 probably, given the way I explain these things, on the microscopic origin of the magneto-optics. What is this effect that occurs when you magnetize your system inside your material that changes polarization, that makes S and P no longer wave eigenstates? Okay. The naive picture that I gave the other day is the presence of a Lorentz force. Okay, that's the classical way to describe the effect. Because you can imagine that you send light along some polarization, you generate an electrodynamical motion of your electrons at the same frequency, which will be parallel to the component of the electric field that is inside your material. You have imagined that at any angle you come in, the angle of the light that the light beam is making inside the material will be mostly perpendicular because the refraction index of the metal is so high that the Snell law is really making the propagation basically vertical here. Okay, so this electric field is shaking the electrons in this way. If you magnetize your system, you develop a magnetic moment per unit volume. It means that I might apply a field if the material is ferromagnetic, that's the peculiarity. I apply a field with a small magnet or with a coil, an electromagnet, so about 10 times, 100 times the field of Earth, something that I can do with a battery if they were charged, okay, and the wire, because of some the exchange, so this quantum mechanic interaction of magnetic moments of atoms, this little field is enough to generate a coordinated, coherent state of magnetization of matter here. It means that if you go inside there is an internal field, which is the field produced by, which is the sum of my little field that I applied, plus the field that all this, in a point, all the neighboring material is generating there. That's huge, it's Tesla's. Tesla's means 10 to the 4 times the field of Earth. So I apply the field which is only 10 or 100 times the field of Earth, and I get inside the material a field which is 2 order or 3 order of magnitudes higher. Okay. If you move a charge now and you have a field like this acting upon the motion of the charge, Lorentz force, you generate also a motion. So when I move like this, a Lorentz force will make the movement do it like that. Okay. I change the direction of magnetization, the movement will be, instead of this, will be like this. Okay. It acquires, I apply the field along one direction, and the Lorentz force is generating this famous component, I said, perpendicular, that combines with the other one, making a distortion of the electrodynamic response. Right. This effect is not in phase, so you generate an elliptical motion of electrons that re-emit lights elliptically polarized. Okay, that's the simple way. Which is wrong. It's true, but it's wrong. So the mechanism inside is not this, inside the material. It's a little bit more complicated, and it's based on a relativistic quantum mechanic physics. Okay, so the electrons are bound to the local environment that is the nucleus of the atom. Okay. Actually, the electrons on the metal, they are not, but when they go by the lattice of the crystal, they feel like remembering, oh, that's my atom, I should make an orbit here. Okay. So there is an orbital motion component in any movement of electrons in a material. Can be a very orbital moment with all the symmetries like S, P, D, etc. Or it can be a vague reminiscence of an orbital origin of an orbital moment when they go by the ions in a crystal. Okay, because in the crystal the electrons we are looking at, more responsible for the optical response in the optical wavelength, are not the core electrons, but are the electrons that are free-like conduction. Okay, and they are not feeling the field of a specific ion, but they feel what is called the crystal field, which has a different symmetry. But so as a symmetry of the crystal, cubic, hexagonal, whatever. So block, waves, etc. But when they are nearby an ion in their motion, which is delocalized, they acquire some orbital moment. So we can talk about a quantum number like the orbital moment, even if in a metal, crystal is so-called quenched, which means it's close to 0 but not 0. All right. And then there is the spin of your electron. So when the electron goes in an orbit, let's say, because of the presence of an orbital moment, in his reference system, it sees the crystal actually moving around him or her. Okay. So you have the nucleus is in a positive charge, so you have a charge that is, according to the electron, is rotating. A charge rotating is like a coil. It generates a magnetic field. This magnetic field has to, so the spins acquire an energy due to this magnetic field, which is a relativistic effect, which is the product of the two fields, cosine the angle. Okay, it means that depending on the orbit, the motion of the electron can acquire an energy or lose some energy respect to the case where there's no this quantum relativistic effect. Okay, this is called spin orbit. That's the origin. Okay. In a sense, this is modifying the orbit like a Lorentz force would do. So Lorentz force, pure Lorentz force, as we think of, is not right, but it's still a good way to look at this. So this energy is in the order of tens of hundreds of milli electron volt. It's not big, but it's there. Okay, we would like to have this energy higher to get the effect higher. That's part of a talk the other day. Yes.
I was wondering, there are some metals that have high spin orbit interaction,
Yeah.
although they are not magnetic.
Right.
What would be the effect?
The effect, unfortunately, is that this thing here, in the determination of Q, this void parameter, comes with a magnetic field. So it means that this S for you will be very small. So you will have a very big prefactor, which is the effect of a large orbit, a very marked orbit. Like, so let's say in a normal metal is kind of wiggling when you go by the right. So this number here is big, all right? And if you make this bigger, okay, you gain here, but your system, being non-magnetic, will have a very low S. You cannot gain on both. In some cases, you can gain something using rare earth. So you make alloys. So it's supposed to be students, and already talking about. So there are some ways for discussing later.
Yeah.
Okay, let's go on. Otherwise, I never get out of this. So it looks like I wanted just to mention that, just to leave you a word, a keywords. This is the very same effect that gives rise to magnetic anisotropy, magnetocrystalline anisotropy. It's the same mechanism that gives rise to anomalous Hall effects, okay, in transport. Remember, optical properties are transport properties, are determined by the electrodynamic response of the electrons. The only difference between conventional transport properties is that we are working at 100 terahertz of frequency, while in our measurements you work in DC, continuous, or up to kilohertz, megahertz, and gigahertz, okay, microwaves. That's the only difference, but yeah, the response gets more difficult because maybe the electrons are not able to fall, etc. But apart from that, the concept is, we are talking about movement of electrons, okay, electrodynamics. Okay, so what you should do to calculate, so now I want to, the idea is to look at the microscopic origin and see how you can get to this macroscopic description, the epsilon matrix, the dielectric tensor, or the conductivity tensor, okay, which is related. We see in a wire that you can. This is more related to the dynamical response, the electrodynamical motion of the electrons induced by light, okay, and then you can calculate epsilon. All right. So this is the sigma, the conductivity at high frequency in our case. Okay.
Excuse me. Why do you have light components for this conductivity tensor?
Because it is the most general case, and treating the most general case. So if you have a motion which is in a direction in space, general, the motion can have a component of x, y, and z. So that's a way to describe the response, the conductivity in all the directions. It's the most general case.
Okay, so somehow it's in the base of the component space.
Yeah, right. Then in the experiment, normally you have one of these, but it's not God-given. When you have a magnetic material and you apply a magnetic field, even if you apply the magnetic field in one direction, and you reverse the magnetic field, magnetization, while reversing, can go anywhere in space. So you might have some moments in time where magnetization is pointing along the general direction.
Is there included in this conductivity the Hall effect?
The
quantum Hall effect?
Yes. If you have a magnetic material, it is in there.
Where? It's the diagonal or where is it?
No, it will be the off diagonal. Yeah, they're off diagonal, right? They're anomalous, the one related to magnetization, right? So, if I were a theoretician, which I'm not, I will start from studying the band structure of my material. So we are talking electrons in a crystal. I will figure out that if the material is ferromagnetic, the band structure can be separated in spin up and spin down contribution. They are not equally, they are shifted. This is called the exchange energy. That gives rise that you have more electrons with spin down than spin up, so magnetization is pointing down, etc. So I will start from here, and then with some theory, I have from this property here, which is the epsilon, so is the energy versus the k vector, the motion. I should calculate the conductivity. From the conductivity, I can get the epsilon, I'll be showing in a moment. And then from the epsilon, I can calculate the reflectivity, and then I have all my problems. So that would be the plan if I were a theoretician. So the key point I wanted to mention is that the purpose of these two slides is that we are not measuring, so now I'm a magneto-optics person, we are not measuring magnetization. In the formula we saw before, there is a Q, which is an intrinsic property of a material, spin orbit, and there is a cosine of M. There's no M. So we are not measuring magnetization. It's important. We are measuring an effect related linearly to magnetization direction. Okay, that's the key point. So you can do the classical magnetometry. I don't know if you are working with magnetic materials. You want to calculate how strong is magnetization. You have special tools for that, where you measure the value of induced dipole per unit volume. Okay. Magneto-optics cannot do that. It's electrodynamics, which is related to the direction of that. Okay. The purpose here is, let's suppose to have a simplified description of a metal, where you have optical transitions from some states in the valence band that has a D character to other states that goes to a different symmetry. Why that? Because if you calculate, because optical transitions are driven by has to obey some specific conservation laws, apart from the energy. Okay, so the energy of the photon should be enough to get from here to here, from here to here. In the process, you have to conserve the momentum and the angular momentum. Okay, that restricts the number of transitions that a light radiation can have. Right. In particular, the selection rules are that the angular moment has to change by 1 unit of h bar. Okay. The projection of the angular momentum along a quantization direction, where we normally call z direction, this is called the magnetic angular momentum, okay, has to change again by 1 unit to conserve the angular momentum conservation law. So energy is one thing, and angular momentum is the other thing. And the spin of the electrons, that it is moved up and down, cannot change. Okay, has to remain the same. So now let's have our hypothetic material where you have a band structure, where you have a D and P states. Why only D and P I'm considering? Because D and P are complying with this requirement. Also here I can have S state, but they are not coming. If I start from here, I cannot get to S state. To get to S state, I have to start from P states. Okay, but I wanted just to show one case, a simple example. So suppose we start from these states, we send light, so these are full state, these are empty, you make an optical transition, and your only states in the band structure you can reach have to have the P symmetry. Okay. All right, now we are considering the existence of a spin-orbit coupling. Spin-orbit coupling depends on this L. So if your second quantum number, so this is n, okay, quantum numbers, principal quantum numbers L, n is 2, just to have a, then we have, sorry, this is the angular number, so this is d is 2, okay, right. Now, if you have spin orbit is splitting, this effect I was talking before, is separating electrons, that the energy of the electron that has a certain spin respect to the plane of the orbit. That means that it's separating states that have a different spin and a different m. Okay, so if the spin orbit is there, this state, it means that the orbit is generating a field parallel to the spin, so the energy is minus m. I'm getting tired. Is minus h multiplied by the spin for the cosine of the angle. They are with a minus in front. So the energy, the magnetostatic energy is lower. So you start from the unperturbed no spin orbit. If you introduce spin orbit, this state has a lower energy, a slightly lower energy than this one, because here it means the magnetic field generated by the orbit is parallel to the spin. Here, the magnetic field generated by the orbit is anti-parallel, so it's a higher energy. Okay, so the spin orbit is separating the state in this way. For one set of spin down. For spin up, it's happening this way. Okay, now if you introduce the conservation of delta m and delta L is already inside here because we go from D to P. If you put delta m, you realize immediately you can go only from here to here. And we use, okay, yes, this rule here has come from circular polarized light. Okay, you can go only from here to here. If you come with the opposite chirality, you can go only to here from here for this band structure. For the other band structure, spinned up, these are the possible transitions. If you combine this, and you say, when I introduce this transition, I have an absorption, and I plot here what I would observe if I change the frequency of my radiation, okay, for one polarization and the other one. When I get to the correct energies, I have an absorption, okay? So if I come with one polarization, I get this absorption, which are due to this transition and this transition. When I come with the other polarization, I can get this and this. But they are occurring at the same energy, very indistinguishable. So it means that the material, the circular polarized light, which is a combination of the two eigenmodes, will remain circularly polarized with the same chirality, because there's no way to have a different behavior or response of material, okay, if I introduce only spin orbit, okay. So microscopically, the modification we are doing is that light is being absorbed and re-emit. So I'm looking at the electric, energy states that produce this transition. That's the quantum mechanical vision of things. But so if you have only spin orbit, you realize you can have two absorption here and two absorption here according to the polarization. But energy, they are occurring in the same energy. It means that there's no distinction between the two absorptions. We're assuming that the cross-section of the process is the same. This can be maybe smaller and this bigger, then you have a difference. So it's a simplified. Now let's introduce only exchange interaction, so magnetism, and no spin orbit. So you can look at this at home. I don't want to go through this.
Paolo, do you want 5 minutes to...
When I get to the right point.
Oh.
Yes. So if I now introduce only magnetism, magnetism is changing the energy of spin up electrons with respect to the spin down. But I leave out spin orbit, so I don't consider that having a spin in one orbit is more or less energetic than having the opposite spin in the orbit, okay? You get a phase, an energy diagram for our hypothetical material, which is like this. And if you do the same conservation for this polarization of light, you get this absorption spectrum. Again, no distinction between left and right polarized light. The material responds in the same way. That means, again, since light polarized circularly is a combination of two eigenmodes, that these are the original eigenmodes, S and P, are eigenmodes. Would be eigenmodes.
I have a question. When you were saying about the measuring the reflectance on all the angles, it's like doing the classical mode of, like just looking by the classical.
You can ask in Spanish if you. No, but I don't want to say. You're doing very well, sorry. Go ahead.
Okay.
Yeah,
So
the angle introduces, I don't know if I got it already, the question.
but you haven't finished my question.
Yeah,
Sorry.
okay, I wait then.
So, it will be like the classical way to see the light. But when you are introducing like the polarization, you are doing like trying to take advantage of the quantum way.
Okay, I got the question already before. Now here we are not looking at the polarization, at the propagation of light. So the plan of the work was this. We have a band structure. We want to calculate the optical properties due to this band structure. And then when you have this thing, you start looking at how light behaves. You go to an angle, to another angle, how it propagates. So the first step is to understand why I have these elements here. So it's not related to what happened to light when it propagates. It's related to light-matter interaction. Light is being absorbed and re-emitted. This is happening with the first layers of atoms, the second layers, and so on. This absorption and re-emission, absorption and re-emission generates the light propagation and the light reflection. We are looking at the mechanism of light absorption and re-emission, which in quantum mechanics is a optical transition to these levels.
But it doesn't go related when you analyze just the magnitude of the reflectance versus like the polarization that it has after. It relates quantum mechanics, those rules of change, or it doesn't.
It does, but you need to develop. You have to go to the micro atomic world, to the mesoscale. That's why you get the epsilon and the sigma. Because to see the effect, you cannot look atom by atom what is going on. It's hopeless. You have to develop some theory, the Kubo transport approach, etc., to get macroscopic quantities that are related to the mechanism. So it's a good question, but it's premature here. I want just to look at how light is interacting with these atoms. That comes later. Yeah. Very convincing, eh? Okay. In the end, you have to introduce both effects. Magnetism and spin orbit is the combination of the two. It's not just one of the two. Because by introducing the both splitting and shifting, you move these peaks one respect to the other. I will give this the PDF, so I don't want to spend now time to see this. Okay, you can look easily, but the message is that if you apply these conservation rules and you make a schematics of energy levels or for an hypothetical material, you realize that you need the presence of the two effects at once to get a different response to elliptic circular polarized light, which is a way to have combination of linear polarized light and not changing the game. Okay. So then, if you have also the transitions, you can look, because I consider just two levels, but you should do this for all the possible combination. You get what is called the joint density of states. From there you can apply some transport rules. So the joint density of states is the Fermi-Gold rule, where you have the cross-section of the property of this absorption, how effective is this absorption. It has a momentum operator and the initial final state wave function. Blah blah blah. You get you have to sum over all the possible transition in your system, and you get basically the real part. So you can get this sigma effects quantities. Okay. This is just repeating what I said. This is what I said. So you cannot have only one thing or the other. You need both of them to get a modification of polarization related to a magnetic field. Okay, and then when you, so using the Kubo or any other approach based on this joint density of states, you can calculate sigma. From sigma you can calculate epsilon, so you get your epsilon for your material. If you consider a case of a material which is magnetized in one direction, the z direction. So now we simplified the geometry just to avoid all these angles of coming in a different direction. Now we have a material which is magnetized perpendicular. Okay, that means we have only these two things here. Okay. So from diagonal, I get off-diagonal elements related to the specific direction of magnetization, and they're coming with the light linearly polarized in one direction. Okay. A light linearly polarized in one direction could be thought as the sum of the two circularly polarized light. Okay. Now we learn from what we studied before that one light circularly polarized, if we are in this condition, will have a certain absorption, so a certain index of refraction, and the other one will have a different index of refraction at a given wavelength. Okay, so it means that the index of refraction from the two polarization will be different when you magnetize. So your light gets in like the sum of two equally circular polarized light, but one gets filling an index of refraction which is different from the other one. So you generate that the two components are, while you cross the material, are attenuated in a different manner, and also they propagate with a different speed and wavelength. So you end up with a phase difference and the amplitude difference and the outside. And the same, since energy has to be conserved, if you calculate the light reflected, you will realize that you have the light reflected will be the combination of two circular lights with different amplitude and phase. That means elliptical light. Okay. So here, at this point, you need to take into account of all the direction you're coming in, and but you are already at this level. You are already classical, where these numbers came from the quantum mechanics. Okay. So everything will be the classical physics of light interaction with crystals, and so you rely on this matrix. This matrix for you is a way to accumulate the quantum mechanical response of your material. So the step before was just let me see what's really the physical mechanism inside. Okay. I think so. That's this. So the summary. So if I have a linear polarized light, I can feel the light is a superposition of light, left and right light, circular, with the same amplitude. I go in the material. If it is magnetized, I have a difference in phase. So it means one propagates slower than the other one. Okay. I have a difference in amplitude. So a different attenuation. So in the end, I started with a linear polarized light, which is the sum of a circular one right and a circular one left with the same amplitude and very well in phase. I get a circular left, which is smaller and out of phase, and the right, which is maybe is bigger than this one, not bigger than the original, but with a different phase. And then the composition of this is an elliptically polarized light along a certain direction. Okay. And all the mechanism is this circular dichroism, okay, at the atomic level, related to spin orbit and exchange energy. So from the epsilon, one can calculate the reflectivity, and I think we can take, before showing that, we can take a break here, 5 minutes, because I need more energy. Do the last effort for me, for you, you have 2 hours. So I had a question for a young student here. I think I should give it publicly answer. So, but I hope I didn't lose anybody of you yet. So and the question was, at the end of the story, why or how, so the Lorentz force vision or approach is not working, but where, how, where it happens. So it is correct, the Lorentz force approach. The problem is the numbers that you have to put in. So the naive story I was telling you is that you have electrons that are moving like they were in free space. You have an effective field which is very strong, and then you apply the rule velocity, let's say Fermi velocity, by h, and no, it doesn't work like that. That's the problem. The effect is the same, but you have to correct the way you would apply quantitatively the Lorentz force effect, and for that you have to work out this coupling, optical coupling. So the Lorentz force is a good way of think of it, but you cannot use the numbers. It's just visual. Okay, you move like this, and all these effects are actually, these atomic quantum effects are producing to the electrodynamics something which is similar to a Lorentz force, provided you could use the right numbers for the velocity, for the h. Okay, that's the connection.
Excuse me, just to go a bit deeper in the question of what is persons, is that I don't know, you have a calculator or measure the
No, I'm an experimentalist.
magnetoresistance, because if you consider only Lorentz force, the magnetoresistance will be linearly,
Yeah.
dependence of the magnetic
Yeah.
field.
Yeah.
And in a quantum regime,
Yeah.
you don't have such a thing. So you have to consider
No, you-
quantization of
no.
energy. So this is a bit quite
Yeah.
to extend the Lorentz force in all the regimes. So it's just a kind of picture that allows us to see what happens visually, but nothing else.
Well, I have to tell that we are looking only at linear effects here. Of course, this is already a simplification.
But then you consider all the kind Lorentz form, you cannot explain or introduce quantum Hall effect at all. So this is the problem.
Okay, because the quantum Hall, you have to look at the coherency. Here we are not. When you go to this epsilon, we are talking a classical, an average, and that's is going to the classic limits. So yes, it was a bad idea to show these things. No, because I gave it the idea that so I wanted to say that the Lorentz force, you have to look for.
I think the question is quite nice,
Yeah.
the both questions.
Right.
Your answer, which is a bit limited, shows that it's impossible to understand this kind of effects only on the basis of Lorentz force.
Right,
There is no
right.
there is
You
no
can
typical
understand
picture.
some, but not the others. Yeah,
Exactly.
yeah,
And
exactly.
quantum picture is impossible to
Right.
to show us, yes,
Right.
unless we.
So in this,
calculate.
yeah, in this treatment, in the end, I don't. When I get to the epsilon, the r, I don't look at the coherency of the states because they are kind of washed out in the calculation of the effective transport using the Cubo approach.
Yeah.
There, I lose this information.
But then the question is coming now, what are the topological effects of this? What is the topological picture of all of this?
I don't even understand the question. We
Yeah.
can talk later. I mean, no, really. If I address this now, I don't move on.
The formula and in the basic levels in the integral quantum collector is related to the Chern-Simons experiment.
I'm not an expert on that, but I think that when you treat this thing, if you were to talk about anomalous quantum Hall effect, etc., you don't go to that transport. They developed based on, I think there is also some exact calculation, but on the most of the papers they take the concept, and then they develop some, how can I say, not empirical, not a kind of empirical formula where you have some parameters, some angle, the whole angle, etc., which is a proportional. It's like using Lorentz force at the second, the higher level. So they have some parameters to link to the experiments, where these parameters, if you want to look how to connect them to the quantum theory, then you need to replace the cube, etc., to get the right things. Otherwise, they use just spin, orbit, and a coefficient.
But by the way, what was the temperature you introduced in the system?
In this case, we don't introduce. This is the only thing here that matters is that you have an order. You have an order, so you have to be below the order in temperature. And then the temperature is not a parameter here in this simplified thing. Yeah.
Okay.
And I think there are also experiments that show that indeed the Magneto-Optics, the only temperature effect you see is related to the M variation. So the fact that you have phonons that can scatter and reduce magnetization, or magnetization is going down. So the reduction of magnetization is a function of temperature. But it's true, there is also a spin orbit effect as a function of temperature that should be considered if you change temperature, yeah. But normally it's not considered. So temperature is not in here, in this theory.
Well, that was like something I want to ask you. Why you're not considering the temperature? Because at some point, I don't know if the material will start to lose the ferromagnetic properties.
Yeah.
So what happened in that case? So
Yeah, you lose the exchange. So as according to what I said
but how
before,
are you sure that
Magneto-Optics
you are?
goodbye.
But how are you sure that you are not changing that ferromagnetic properties when you heat up with your laser?
And you do.
What?
You might do that,
Okay.
right? That's, for instance, is the optical ultra-fast switching
Yes.
is based on that you bring the sublattices, because they are working with composites that have different gadolinium with iron or cobalt, and you bring very quickly in the femtosecond time scale the system out of equilibrium, and you can lose you can also increase the temperature of the lattice beyond this Curie temperature for one, and you generate effects. But I don't know if I understood. So the answer is, if you are far away from a critical temperature,
Yes.
okay? So we are talking about technologically relevant material in a conventional way. So we are away from Curie temperature of the material. So you are, that's, I don't know how many can follow. So you have if you look at M versus T, you start off with a very, a decrease of M versus T, which is very low, and then you get, when you go to a critical point there, you are going down quickly. So that's the Bloch law. You generate. So it's the interaction of magnon with phonons. Okay, that gives the reduction. The anisotropy is also has some change, but you are in a region where if you change, you need to change by 100 degrees the temperature to get very different, appreciably different effects. Okay, so we are working in a regime where temperature variation is not modifying too much all the physics I mentioned here. Of course, when you go close to the transition temperature, not only the magneto-optical effect should go away when you lose all magnetic order, okay, but also the response will be different. It's actually a full field of research that was proposed by me actually and others in already 10 years ago, but we never really. Some studies were done. What happened to magnetics and magneto-optics near in this particular state of matter, magnetic matter, around the critical temperature? So I don't have an answer. I expect that this picture will change. These Q numbers will be different somehow. But at a certain point where we go away, so you can use magneto-optics to measure where is the Curie temperature. Then you might have a scaling law, which is not the scaling law for that spin system. Okay, the critical parameter can be slightly different, and that could be because you are not measuring magnetization, but you're measuring electrodynamics. And okay. So here we are.
The pointer is working.
Coffee is there.
Yeah,
No, no, the pointer. I think
Pointer is working. Mine is mine,
Yeah.
but it is not working here. You can see.
No, but it's not a matter of.
The exchanger. Yeah. Okay, so after this short, not so short journey into the microscopic origin of the effect, so it's not a Lorentz force, but it's similar. Let's go back to the origin where we started from. So we know now that if the reflectivity in case of a magnetized system have off-diagonal elements. That's the key point. So we go in with a certain field, we go out with a certain other field, which is a mixture of the. So we go in with a certain field. By doing the multiplication, this is a reflected field, which would be a combination of both possible polarization, and then you calculate. So the full thing is to calculate how big are these polarization change. Okay, that are originated by that effects we talked before. Here is an expression when you the case I treated so far was perpendicular incidence because that's easier to treat. But if you go in at an angle and you take into account of let's say complex Snell refraction, okay, you can calculate. So there are expressions for this R, PP, RSP, RPS, etc., which are this one, okay, where θ1 is the refraction angle, so the angle that the beam will be taking inside the material. θ0 is the angle of incidence. And then we have the epsilon of our tensor, okay? And that's the way it looks. So n0 and n1 are the square root of epsilon 0 and epsilon 1, so the refraction index of the material. So in particular, n0 will be a real number, but n1 will be a complex number because you have also not only the light go a different speed, slower, but also it's being absorbed. So when n is complex, you have a refraction and absorption, and so on. And so these are the formula you might use if you want to calculate beforehand what is going on when you reflect light from a material. So you need to know the properties of the material. These are summarized by this epsilon, so the optical properties. By knowing the geometry of the experiment, you can calculate this. But as I said, we need to measure these quantities. Okay, this is to connect measurements to theory. That's the way. The point here, the key point, which is a very powerful properties of magneto-optics, is that if you make the effort of measuring these three things, you get information of direction in space of magnetization, because you can, if you measure this by these relations, you can get mx, mz, and my. Okay, it's a function of field.
So, why are you not considering the magnetic permeability if you're talking of magnetic materials?
Good question, very good. Was suggested. Okay, that made me a lot of troubles when I deliver. I'm not an optics guy, I'm a magnetic guy. So when I go to now I'm going to optical conferences. Anytime I talk to this Lorentz force, my magnetization, the dipoles, everybody's thinking of the optical magnetic dipole. Okay. Okay. All right. So here, magnetically, the materials, the response of magnetization, the static orientation of the spins inside your material, if you want to shake them, okay, you can do that until, let's say, 10 gigahertz. So if you find a way to shake with an electric field and try to change magnetization of a material, you can do as fast as 100 picoseconds. Okay. Faster, the material is not able to follow. Okay. Optical frequencies, we are talking about optics, we are at 100 terahertz. Okay. 100 terahertz, the magnetic field of the light, which should try to move this magnetization, that's the magnetic permeability is talking for, is order of magnitudes faster than the fastest response that metals can have magnetically. So the magnetic field of light is doing nothing on the magnetism because it's too fast. So the magnetic permeability in optics is 1. Okay. The electrodynamics is not magnetic, it's the motion of the electrons. The motion of the electrons can go up, as we know, attoseconds probably. So there you have an epsilon, which is not 1. It actually has a complex dependence on omega, with numbers, etc., etc. Okay. But magnetically, our system magnetically is inactive in terms of light-matter interaction. Okay. There is no possibility of shaking any magnetization there. Too fast. Good. So the fact that in principle, if I measure these numbers, I can retrieve all these 3 cosines is super powerful. Because when you do a magnetic study of a material, you want to know what happened, you want to track how magnetization is moving when I apply a magnetic field along a certain direction. Magnetization can do very weird things. It's moving in space. When you measure an hysteresis loop, you normally measure one component of M, which is normally the one parallel to the field you applied. And when you have a switching of magnetization, you just measure a projection of the vector on the direction of the field. You have a very limited information. If you do magneto-optics and you do a full magneto-optics, you know exactly at any moment where magnetization is pointing. Okay? This is called vectorial magnetometry. And with optics, without touching the sample, because you are sending light, without breaking the sample in small pieces to be put in a very difficult, very complex system where you need to rotate them to get the different components, blah, 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 you have a possibility of determining what magnetization is doing at any moment as a function of the applied field. As direction in space. You don't know the modulus, but the direction you can get it. That's one powerful properties. Okay, so we don't want, so the smart guy that was mentioned before, will try not to measure this RPP, RSP, RPS all at once by doing all the large number of the experiments. We will try to set the system evolving along certain specific direction, control experiments to determine only one component and the other one at a time, one at a time. Okay, that's why you find this nomenclature in the literature where they talk about polar Kerr effect, longitudinal Kerr effect, transverse Kerr effect. This is just a way to isolate the effects you have in the RPP, the RSP, and the RPS to get one at a time, just not to have the most general behavior in one experiment that requires a lot of work to retrieve information. You can design the experiment to have this dielectric tensor and the reflectivity modified in a controlled way. You don't know the numbers, you need to do the measurements, but at least you know you're dealing with one of these elements at a time, okay? But the purpose, and where these numbers come. So when we talk about polar effect, polar magneto-optic, when we come with a linearly polarized light, and we apply a magnetic field to induce magnetization perpendicular to the normal, so parallel to the normal of the sample. Okay. So having magnetization in that direction will involve one of these RPS, okay, that the result by measuring the ellipticity of the polarization of a reflected light, we can get that number. From the get number, we can get the MZ. If you do another experiment, you can detect this component, okay, the effect of on the light due to this component. So you measure the elliptical polarization, and from that, coming back, you get the information about the component of M in this direction, and so on and so forth. So we design, let's say, experiments to get simplified process. Okay. Okay, the whole thing then is to polarize light linearly, send it on a sample. The reflection or the transmission in Faraday will produce an elliptically polarized light. Okay. And then we want to measure this ellipse. What does it mean measuring an ellipse? We'll be measuring some parameters that tell us how the ellipse is done. Is a vector rotating in a plane, so you need two parameters. You can pick any parameter at will, but the most, let's say, sensible parameters is I came with a light polarized in this way, and I came out with a light doing this. So the first effect that I have an elliptical light, which the major axis is rotated by an angle with respect to the original direction. Okay, let's use this as one parameter characterizing my ellipse. Then, if it were just linear, the field will do this, but now the field is doing this motion. So the other parameter would be the ratio between this axis and this axis, which is exactly this angle here, which is called ellipticity. These two numbers tells you all about that ellipse. Okay, you can pick other numbers, but these are the numbers that normally we use. Okay. If you now assume that these angles are small, this is an exercise for you. You can work out how this using the geometry, you studied, I don't know what year, first year, second year, analytic geometry, you can get out how these angles are related. So knowing that this light is coming from a combination of reflected P light and reflected S light, you can correlate this angle to this RSP and RPP, okay? And by using the approximation that these angles are small, so you end up having a tangent of 2 times this angle and the sine of 2 times this other angle, okay? If these angles are small, which is good for this mathematics, but is bad for applications, you can approximate the tangent and the sine with the angle, and you get this relationship, okay? So all in all, at the end of the story, the angle, the two parameters that we need to measure to characterize the polarization of light, or the reflected light, are these two angles, okay? And they are related to the real part of these ratios and the imaginary part of these ratios under this approximation of small angles, okay? This is just analytical geometry. Can I go? Believe me, if you need to look, you can do on a piece of paper. I did it. Every year I go through this myself, like a student, because it's very difficult to remember the passages. All right, so we need to measure these two numbers. And actually, if I measure, suppose now I can measure these two numbers. Okay, measuring these two numbers is measuring the polarization of light. Okay, it's doing what is called polarimetry. Okay? I'm doing polarimetry when I measure two angles. I'm doing for a certain wavelength. Okay? If I change the wavelengths, the response will be different because the epsilon is frequency dependent. When you will do spectroscopic polarimetry, which is very fundamental for plasmonics, because you want to see what happens if you change your wavelength. But now fix the ideas and think that they are using one wavelength. So these are epsilon, which are specific numbers. So these angles are given for a certain direction of m. Okay. Now that's the power, because I can measure this angle as a function of magnetization. So m will be changing. I can measure what is called the response, the magnetic response of your material as a function of field. So I can measure hysteresis loop. Okay. So primarily, Magneto-Optics was very successful in the last 30 years, let's say, for magnetic characterization, especially when the industry moved to computers and hard disk drives, etc. You need to know if your material that you are using to record information is working properly. So you can break it and go to a magnetometer, etc. Well, that's really destroying the material. Why? Now we can have your hard disk, scan a laser on top of this, apply some magnetic field, and you can measure magnetic property, measuring light properties. Okay, there are very several advantages because you can focus light, you can have a spatial resolution, you can do microscopy, you can do everything without destroying the material, without even touching it. The material can be inside a vacuum system, and you can go through the wind at some viewing port and measuring. Okay, that's so the fact that we cannot measure m as an absolute value is a loss. It's a price that is worth paying by using optics, because the number of advantages are enormous you get. ¿Me vas a enseñar algo? No?
10 minutes.
10 minutes. Más 5.
Sí, pues,
15
pues,
minutes.
sí.
Okay, so it's somehow related also to the previous questions. Everything we developed so far with the Queen this is another way to write it. So you can normalize everything to epsilon diagonal, so that's just not to confuse you. This is what we talk about so far. Okay. In reality, is if you take into account, if you go more in depth, you realize you can have second order effects, third order effects that are smaller and smaller, but they are there. Okay, and everything can be calculated from the band structure, etc. So sometimes when you measure your hysteresis loop, you find some asymmetries in the response. Okay, 1 second. The fact that you have a response like this, which is symmetric respect to x and y, okay, is again coming from the time reversal breaking symmetry, this non-reciprocal propagation of light. Okay, so the hysteresis loop, so the response, optical response, and the m basically versus h has to have a symmetry, has to be symmetric respect x and y. Okay, you have to be able to flip this along the diagonal. Okay, if the effects are linear. Okay, so looking at the hysteresis loop, it has this symmetry. You know that all the theory I talk about having linear effects, measuring the mx and is working. Often it doesn't work. You do an experiment, you do something like this, which is breaking this symmetry. So here is the h equal to 0, and this is m equal to 0. So you see that the symmetry is not preserved here. So the symmetry that would come from this part cannot give this type of asymmetric behavior, left, right, top, down. Okay. If you impose that symmetry and you look, so by summing whatever is on this side, change of sign to this one, you can sum and do the difference. You can isolate the symmetric part and the part which is breaking the symmetry, which it looks like this. Okay, you realize that this thing with the noise is a system, as a symmetry. So this signal which is spoiling or destroying this symmetry has this form in this case, for instance, in this very common case. And apart from this experimental error, he has this symmetry, let's say. So this symmetry is even respect to x, the y-axis, okay? It means it has to come to be proportional to the m square, is a second order effect. So anytime you have second order effects, you would expect some asymmetry in your loops, in the response of m versus h, which in our case is rotation or ellipticity versus h. Anytime you break this left-right top-down symmetry, it happens normally with a component of the response which has a x symmetry, okay? And the only way to get this having second order, which makes sense because we did a linear first order development or theory, but you can expect having higher order, okay? The good thing that if you know this, and anytime you see something like this, instead of saying, of crying, what on earth is happening here, you know that if you impose a symmetry, you actually are gaining something from this loss. You can get the linear response, which is the direction of m, and you can get also m square effects, which are sometimes interesting, especially for magnetoresistance, for instance, because they can have a special effect on the magnetoresistance response. So, okay, we need to measure polarization. We have detectors. Detectors are like, now we go to the technical part. Wake up. Good. Now we get to the hands-on thing. So I hope I convince you that we need to measure polarization. Polarization is coming, change induced by magnetization is coming from very subtle quantum effects, etc., etc. And if we can do these measurements, this polarization measurement, we have a very large number of information or quantity of information that about magnetism and optics at the same time, which is very useful without destroying a sample, without touching the sample, at the speed of light. So you can study even the response, the dynamical response I was mentioning before. So magnetization can change quickly up to the gigahertz. There are not many techniques that can measure this change. Optics can do, because optics is terahertz. So measuring something at gigahertz or 100 gigahertz is easy, okay? All right, but the key point then is you need to measure polarization. And we are using our eye. A detector is like an eye, measuring intensity. So the whole work that an experimentalist have to do is to develop a setup that can measure polarization with the precision needed, okay? And then design the orientation of H, orientation of the sample to get this RPS, RPP, okay, smartly instead of measuring all mixed all together, okay? But the first thing, we need to measure polarization. And these effects are very small, milliradians. So are a fraction of a degree, okay, very small. That's why you want to use plasmons to enhance them. So we need to measure with high precision very small quantities. And there are quantities that are not directly detectable by a detector. Detector measure intensity. Okay, but we know the Malus law. We know that we have, if we want them, if I have, suppose I want to measure the intensity of this on my laser, I can polarize the light, suppose it is polarized. Then I can put a second polarizer, which is an analyzer, okay? And by rotating this, I can get to a situation where I get extinction, when I get maximum signal, which is a maximum signal, extinction, etc. Okay, with a very known law, which is the cosine square of the angle of the rotation of the selective polarization of the polarizer respect to the electric field oscillation. Okay, we have the malus law. So if I suppose I send the light polarized like this, and I put a polarizer like this, I should measure 0. Okay. Now I put inside my magnetic material, which is I have magnetized, and then the polarization is changing. It acquires. Remember that at the very end of the whole story, you generate. If you go with one polarization, you generate a second component. Measuring this rotation and ellipticity means to measure this second component, how big is respect to the first one, and its phase. I'm a big fan of phases. Yeah? All right. Okay. About the phase we talk later, but at least the fact that I generate this perpendicular component, I could already see with a simple setup like this, because the light is coming, no magnetic material, I put my polarizer here, nothing is going by, and the detector, your eye, measure 0, just the noise. Now I put my magnetic material, I magnetize, I generate some change in the polarization, so I generate some component here. That component goes by, and you have an intensity of a detector. Okay, so you know, and you know also with which law the generation of this second component of the electric field is related to polarization. So by using a polarizer and a detector and measuring intensity, you can trace back to changes in polarization. Okay, the first thing that the challenge is designing a system where you can deal with intensity in the very end, okay, intensity of light, and get this intensity carrying the information about polarization. Okay, all the design of magneto-optics setups is that. Okay, rotation is easy. That's already a way to measure rotation. So measuring the amplitude of this additional component, which is created by the magnetic material, when I started from this, that ratio, how big is this respect to this in modulus, that's the rotation, the theta angle. That's easy, a polarizer. You don't need much more. But I said, phase is important. We need to measure phase. Phase, the fact that this second object is not oscillating in phase with this, that's the generation of the elliptical light. The phase is the ellipticity. So the measurement of the ellipticity is a measuring of the phase delay of the generation of these two components. So we need to have a way to do that using a detector. Easy. Because we have crystals that are anisotropic. They don't break the time reversal symmetry, so they are not useful for isolation. But the crystal is not cubic, so if I have a vector of light which is propagating along a certain axis, it goes with a certain index of refraction. If it goes along the other axis, it goes with a different index of refraction. Okay, there are birefringent. Okay, the ideal material has to be transparent. We don't want to have also dichroism, so differential absorption. That we're gonna screw up everything. But so transparent materials, calcite is an example. They have two optical axes with different n here and here, and that means that the light with this polarization will go with a different speed. As I mentioned the other day, depending on the thickness, I can generate the retardation I want. So I can modify polarization of one bit coming in a given way. So if I know that my experiment is done with a certain wavelength, 633 nanometers, red laser. I can buy a crystal which has this property and has a thickness such that if you have a field at 45, it generates exactly a quarter wavelength retardation of one component respect to the other one. Okay, you buy it based on the anisotropic properties of material, transparent. So you do not attenuate light, you just modify the retardation. And you will say, well, you are crazy. You have your material that already modified polarization, and now you want to modify even more, so you are going to lose the information. No, because if I do the proper way, I will show you I'm not losing information by doing this. So, electric light polarized goes through my magnetic material, which is magnetized in such a way that generates a second component out of phase. The light will be elliptically polarized. I want to measure the ellipticity, okay? And basically, if you look at this diagram here, if this light goes through a crystal like this, where you have one index of refraction here, different from this one, you get out to this new field. Again, an exercise to do, it's just multiplying matrices here, there's nothing to do. And this field, from this field, if you measure then this field, you can get this angle ni, which is actually related to the ellipticity. So to measure ellipticity, you have to disturb ellipticity by adding a system that changes the delay between two fields perpendicular to each other. You have to add some wave planes, okay? So if you put after this transformation, so basically what a crystal like this placed after this will do. That's is going to make crystal clear why this works. So what we are doing is the following. Light, material, so now we have two fields out of phase. So you have this electric field describing this ellipse. You put this crystal, okay, and you rotate this crystal by introducing this ellipticity as two components that are out of phase, okay. By rotating this one, basically what you are doing, you are changing the retardation that was introduced by the magnetism in such a way that you compensate it. So you go from something like this to something like that, which is linearly polarized. How to measure a linear polarized light orientation? We do like we did before. So you convert an ellipticity in a rotation. You know how to measure rotation because it is measured by a polarizer. By measuring this rotation is related to ellipticity. So basically you use a retardator to compensate the retardation introduced by magnetic material, which means rotating it. This rotation is the information of the ellipticity. How much you have to rotate a crystal that has known properties and introduces a phase delay to compensate the effect of your magnetic material. That's the information of the phase. Okay?
What kind of crystal are you using there?
Is calcite.
But why are you not using like a liquid crystal retarder?
Because you can do, yes.
Yes.
You can do. Nowadays, you can have actually. This is not the point. This is not the point.
Yeah.
How you make the final experiment is up to you. Of course, if you have a liquid crystal device or an active device, the guy who's sleeping was asking me about the active device. You can have a quarter. You want to have a quarter wavelength behavior. You can have it. So that if you want, you have a crystal, you can work at one wavelength. If you want to work at more wavelength, you like to have this tunable. That's the way to do it. But there's no reason. I mean, that's it's not about the material I'm using. It's the property. I want to compensate a retardation, and you do which way, whatever way you want it. There are several ways until 30 years ago when I was working, are only crystals. Now there are many more ways. Well, we have also pocket cells. That's very nice. There was a question?
No, I have a quick question. For a specific material, you have to rotate this crystal, right?
Mhm.
If you change the material, then you have to change the rotation until you get linear polarization.
Mhm. Yeah. But in the end, I don't do this experiment. I do it a different way. Time.
5, please.
Okay. So basically, we do the experiment more in a better way. 5 minutes are enough because I'm done. All right. So we learned more or less how we can measure a rotation. For that, you need just a polarizer. How to measure an ellipticity, you need a wave plate to generate a retardation that can be adjusted by rotating the wave plate. So you reconvert the elliptical light in linear, which will be rotated, and this rotation is epsilon, okay? But in the end, we are talking about fraction of degrees. Whatever you do is getting out the numbers, the intensity you are measuring will be small numbers, very small numbers immersed in the noise, okay? I don't know who was the other day to my other talk when I mentioned about the ellipticity crossing zero, and I mentioned, oh, everyone who do measurements knows that if you have a signal that can be null, going to zero, that gives you an incredible advantage in measuring that quantity with a very high precision. Okay, so the other art you have to apply in optics is to get compensation effects, because if you can have a signal which you want to measure that you can combine to another one to get zero, any variation of that signal will give a variation of a zero, which is super easy to detect precisely. Okay, right? Because rotating the polarizer, you cannot rotate, or the lambda, you cannot rotate with a precision of a fraction of degree. Forget about it. So the trick is basically this one. Actually, with the very same setup, this is very cheap, can be implemented with a few €1,000, some millions of, okay, but still it's cheap, is a way to measure rotation and ellipticity with a device where you don't have to change anything. You put your lambda in a specific direction and you measure through another crystal. The price you have to pay is to have a crystal that separates one polarization from the other one when the light goes through. And these are materials that exist also. They are the one used for the polarizer. Okay. If you do that and you use two detectors and you make the difference between these two signals, you are done. You can measure the two angles of rotation of the ellipticity with a precision which is orders of magnitude better than putting the polarizer and the lambda and rotating. Okay? Unless you do a continuous rotation with many measurements. Okay. So this is what happens when you send the light through the magnetic material. It becomes elliptically and rotated. Okay. If you invert magnetization, the effect is inverted. That's the hysteresis loop that we saw. There is a sign change. So you want to measure this ellipse. It means rotation, how this long axis is rotated with respect to the original polarization, and how is this short axis ratio with the long axis, the ellipticity. Okay. Unfortunately, you cannot do it in one shot, but if you take a lambda for the quarter wavelength plate, which is the same material with a certain thickness, that generates a retardation of a quarter period from one beam going from one axis respect to the beam going to the other axis, and you rotate exactly at 45 degrees with respect to the initial polarization, it's easy to see that if you send a linearly polarized light through such a device, you get that this light has one component along this direction and one component along this other direction, which are identical. They are dephased by p4, p half, or lambda quarter. And then the light coming out will be a perfectly circular polarized light. So if you want to create circular polarization from linear polarization, you take a lambda 4 rotated by 45 degrees and you put it here. Now, if I change this polarization due to my magnetization, what I'm doing, if I go through this, is that I go from this circular polarized light to a slightly elliptical with m plus, and elliptical in this direction with m minus. So if you insert a lambda 4 in the path of light, the magnetization will distort the circular polarization in elliptical polarization, okay? And why this is an advantage? Because now, if you go through this device, in the original case, the circular polarized light has the same amplitude of P and S, so you have the same intensity here and here, you have a 0. Any distortion here, small as it can be, it gets a decompensation of intensity. So you get a signal out of 0, which is very precisely measurements. You can measure milli-degrees with this device, okay? I leave for you to show or imagine what happens if I put a lambda 2 wave plates. So it's the same material, but it's thicker. So now one component is retarded by half a period with respect to the other one. It means it's the same crystal, but you make it longer. So you accumulate retardation. Okay, you can buy it. If you rotate at an angle with respect to the initial polarization, the polarization is simply rotated by twice this angle. So now I go in like this. I put this at 22.5 degrees. The light out will be 45 degrees rotated. No magnetization. It goes through the very same prism. You get the same component S and the same component P in intensity because it's 45, so this component is as large as this one, 0. Now you apply magnetization, you change the polarization, and you generate this change here. So the lambda half rotated by 22.5 degrees is just taking this thing and rotating by 45. By doing this rotation, the component S and P are no longer identical. You measure an uncompensated signal with a very high precision. So that's the way to measure small polarization changes below the degree using static materials. No modulation, nothing. I just put a lambda over 2, a lambda over 4, this particular crystal, and 2 detectors. Okay? Last. Okay.
We have time for short questions, even in Spanish, if you want. So, ¿sí?
¿En español o...?
Sí, puede ser también. Si quieres practicar inglés. ¿Quieres practicar italiano?
Digamos que en el efecto que nosotros describimos básicamente la interacción del material con el campo magnético mediante un tensor de permitividad en este marco.
Ya has empezado mal.
Bueno, ¿cómo se escribe la
decimos, el campo magnético induce un cambiamiento de emanación en el material y es ese que estamos tratando de, es el efecto magneto-óptico. El efecto de cambio de polarización debido a la interacción de la luz con la emanación. El campo magnético es solo el estímulo para cambiar, para inducir una emanación en el ferromagneto y para cambiarlo. No es el campo magnético que aplico yo que produce el efecto que...
Sí, pues.
Ok, vale.
Listo, entonces ese campo magnético, bueno, cambia ahí, o sea, el estímulo que que se coloca ahí en el material, ¿cómo se puede escribir? ¿En términos de qué?
Básicamente simplemente introducir una energía, ¿vale? Que es la energía de interacción de un dipolo magnético con el campo magnético, que es menos el momento magnético, m, como vector, producto escalar, dot, el campo magnético. Sí, entonces m, h, cosine del ángulo que forma, ¿vale? Entonces, cuando aplico un campo magnético, para reducir esta emanación, esta energía, la emanación se va dirigiendo hacia el campo magnético. Entonces, el coseno es máximo, entonces la energía que tiene un menos es mínima. Entonces el efecto del campo magnético es un par, un torque. Desde el punto de vista energético es minimizar esta energía magnetostática, que es menos m h coseno teta. Con el menos de adelante, la energía mínima tiene el coseno teta igual a 1, ¿no? Que es ponerlos paralelos. Entonces tú estás aplicando un campo aquí, la emanación quieres que se vaya aquí. ¿Cómo va aquí? Es interesante, ¿eh? Porque eso es un giroscopio. Pero vale, al final estás haciendo esto.
Bueno, ¿otra pregunta? Sí.
Paolo, you show us on the longitudinal and polar curve effect that we have ellipticity, yes, after the reflection with the sun. But in T-mode, you only have, I don't know, it looks like you only have the intensity. So we are only measuring eta and not theta k and epsilon k in that case.
Is already the next lecture.
Okay.
But the answer, I can give it quickly now, is that the light being reflected in that configuration is you go in at an angle with the light polarized in plane of incidence, and you magnetize the sample in plane but perpendicular to the plane of scattering. Okay. The effect is the light reflected is same polarization. Okay. It doesn't change polarization, but is not in phase with the incoming light. So you can measure two things. Always, the second information is hidden. In the longitudinal and polar is coming out because the light becomes elliptical. That's in intensity and the phase. In that experiment, apparently you have only an intensity because you don't measure that phase. But that phase can be measured. And sometimes it's much better measuring that phase than the, I will show how to do that. But there is a phase also there. But in principle, where you don't need, you just measure the intensity. That's why it's even cheaper doing measurements using the transverse smoke effect.
Okay, let's thank the speaker again and